Often we want to quantify how well our model describes some underlying data set. And one common way to do that is through what, well, formally is called the coefficient of determination, but you may know it more from its informal name of an R-squared statistic. And this is just a proportion between 0 and 1. A proportion of what? It describes how much of the variation in the response variable we could explain with variation in the predictors. So how much of the response is determined by changes in the predictors. If we get an R-squared value of 1 or 100%, this means that all of the changes in the response are explained by changes in the predictors. So if this is a linear model, all of the points would fall perfectly onto a straight line. At the other end of the scale, an R-squared value of 0 says there is nothing in the predictors which can explain any of the variation in the response. This is all just a cloud of points without any explanatory power in our predictors. So obviously, in general, values of 0 or of 1 are exceptionally rare to see. But it does just describe how much of the response is determined by changes in the predictors. What it isn't doing, however, is telling us anything about whether or not we feel that their variables are significant in the model. So we can have models which we have strong evidence that we should include the variable, even though it's only determining a small amount of the changes in the response, and conversely ones that might have a big impact on the R-squared, but in fact may or may not be significant. We now need to introduce a bit more statistical definition and notation. So if I've got a data set, I can calculate the total squared variation around the mean as SST, so the sum of the squares in total. So this is squaring how far above or below the mean each observation is, so the sum of yi minus y bar squared. Now if I've got a model, I can calculate the same thing, but rather than calculating the difference between each observation and the mean of that variable, I calculate the squared error around the model, so yi minus the predicted y hat squared. And that's SSE. And the last of these is the sum of the squared deviations to the regression line, which is just the difference between these two. So SSR being equal to SST minus SSE. Now, the proportion R squared is just this, how much of SST is explained by SSR. So SSR divided by SST. Although we'll tend not to calculate it that way, we'll tend to think of it more as 1 minus SSE over SST. So those definitions are obviously equivalent. But what does this mean visually? Well, if I take a very simple data set with 4 points and a trend line, if I calculate the residuals to that trend line, if I take the sum of those squares, those are the sum of the squared errors for this. So I have the sum of epsilon I squared is the sum of yi minus y hat squared. What I want to do is I want to compare this to the, I suppose, the most sort of blind, unthinking model of saying, well, all of the responses I think are just going to be the average y bar. Now I can calculate the errors around if that were my model. And of course, the sum of those yi minus y bar squareds will just give me SST. So what I really want to be doing here is to assess an R-squared, I want to say, well, compared to just drawing a horizontal line, how much of the variation is my model capturing? And obviously, if my model is not doing any better than just a simple everything's average y-bar model, then it's not capturing much of the variation. Versus if it's really capturing how variable y is in a way that just drawing the mean as the trend line didn't, then obviously I'll have a much larger R-squared value, saying that this trend line I'm working with is capturing all of that variation, or much of that variation. So it's really a comparison between these two. Now, one thing I would say is you may see some textbooks or some other sources that define SSR not as the difference between SST and SSE, but as in fact yi hat minus y bar squared summed. Now, the definitions are the same, but it's not obvious that these two definitions are the same, at least not at first glance to me. But if we actually work this out, we write out the two terms for SST and SSE. I'm going to add in a term and subtract it. I'm going to add in to the first term plus yi hat minus yi hat within the squaring. And this allows me to regroup and then expand the terms. And so what I can easily see is that this does collapse to the same thing, but only if the sum of yi hat minus y bar times yi minus y bar, if that sums to 0. And again, it's not instantly obvious that that condition will hold. But I know that the parameters have to satisfy that beta hat minimizes this sum of squared residuals, and that the sum of the residuals is 0. If I work that through, the derivative having to be 0, and I apply the other constraint as well, then a little bit of rearrangement does in fact give me, let me get there, does in fact give me that this term, that the y hat minus y bar times yi minus y bar has to be equal to 0. So the two definitions are equivalent. I will tend to work from calculating it in terms of subtracting the sums of the squared errors rather than this other form. But if you see different textbooks with what look like different definitions, they are in fact the same. So if I want to actually assess a model fit, the hypothesis which I would be testing is the null hypothesis, being that all of these slope terms are 0, so the model can be explained just with an intercept. And if I want to assess that against the alternate hypothesis that no, at least one of these predictors, x1, x2, or whatever, is necessary, that it captures some variation in the response y, that the null model of just the intercept term, just the average y, it captures variation that null model doesn't. I want to work out the proportion of the variation in the data explained by the null model. If I work out this SST, then my null model is just that y bar, which would be my intercept term alpha. And then I want to work out how much squared residual there is in the model, and want to work out the proportion of one of these terms of the other. So if I assume that the residuals are independent and normally distributed, and they have equal variance, then what I have is I have a sum of independent realizations of the square of a standard normal, or sigma squared times standard normal. So what I actually have there is, under this distributional assumption, that SST should be sigma squared times a chi-squared variable with n minus 1 degrees of freedom. Because I have n variables I've added, but there is the constraint that I know all of the yi's add to give, well, an average of y bar, so they add to n times y bar. So I've got one constraint for the n variables, so I've got n minus 1 degrees of freedom. Similarly, if I work out the squared variation around the fitted line, I've got a similar idea, but I have fewer degrees of freedom, because the fitted line, well, I can move the alpha, but I can also move each of the k beta parameters as well. So here I've got n minus k minus 1, that I've got not just one constraint, but I've got k plus 1 constraints. So this will give a chi-squared with n minus k minus 1 degrees of freedom. So the variation explained by the model will be the difference between these two. So it should be a, well, sigma squared times a chi-squared with k degrees of freedom. So what I want to do here is I want to say that under this null hypothesis, that I'm comparing the null model with everything is just the intercept term to the more complex model with all of these slopes in there, I want to see what proportion of the variation in the responses is characterized by, is captured by the variation with just this null model. Now I know that the weighted ratio of two chi-squared variables is an F distribution. What this does mean is that I can start to say, well, SSR over K divided by SSE over n minus K minus 1 should be an F statistic, or should be F distributed, with K and n minus K minus 1 degrees of freedom. And then you would reject that if the proportion of variation explained by the fitted regression line is greater than the critical value. So if I'm explaining much more variation that would happen just by chance under the null model, I'd reject the null. Otherwise, I'd retain the null. And that does require the assumption of normality of residuals. And this is really the bedrock of what's often called ANOVA, or analysis of variance. So if we've got categorical variables, this is really what's done in an ANOVA, which again is a technique we'll see a little bit more of, but you may already have heard of.